We know the internal member forces are shear, bending and axial. You hopefully all realise to calculate those three forces, all you need to do is create a free body diagram, cutting through the beam at that point, and you simply use equilibrium to calculate those three internal forces. And I call them forces, or actions, internal actions, because they are forces as well as moments. Now, as you know, when something bends, the curvature varies throughout the beam, so our bending moment varies throughout the beam, which is why we need to be able to draw bending moment diagrams, rather than just calculate the value at 1 metre, 2 metre, 3 metre, 4 metre, 5 metre, 6 metre. Very tedious, so we draw bending moment diagrams. So what I did was I actually worked through the equilibrium of a small section of a beam and came up with the fact that there are these wonderful relationships between bending and shear. And based on these wonderful relationships between bending and shear shear force diagram being so easy to draw, we can utilise our free body diagram and very quickly actually come up with a bending moment diagram. So the relationships here that we will utilise are the fact here that, oops, no, didn't get the pen working yet. The fact here that when we draw our shear force diagram, as well as it being the shear force diagram, it is the value of the slope of the bending moment diagram. So if our shear force is positive, that's telling us our bending moment has a downward slope. Now once again, positive normally means upward slope. You have to remember we're drawing our bending moment positive down. Okay? So a positive shear force means when we come to draw our bending moment diagram, it will be sloping down. A negative shear force means when we come to draw our bending moment, it will be sloping up. So just by working through that relationship, as well as that, because V is equal to dm dx, the converse is true, that your moment is equal to the integral of V, which is the area under the shear force diagram. So again, you want to know the value of a moment, we just look at the area under our shear force diagram. And because our shear force diagram is either constant or triangular, we can very easily work out those areas, we can work out the values of the moments. Okay, so I think where I left it, where I very quickly showed you the relationship between load and shear, that there was also this relationship here, that the slope of the shear force diagram is equal to W. W being our uniformly distributed load if we have one. Thus, when we have no UDL load, as in the case here to the left, where you only have a point load, the slope of our shear force diagram will be 0. However, on the right here, where we have a uniformly distributed load, that means the slope of our shear force diagram, slope of this line here, will equal 5 kilonewton per metre, because our shear force is reducing at the rate of 5 kilonewton per metre. So quite often on exam papers, what I do is I draw these wonderful shear force diagrams for you, and I say, tell me what the corresponding load is. So if this one actually, say it's stepped down further here, so say this was our shear force diagram, you would say, okay, I have a UDL load. It's sloping down, so I know I have a UDL load through here. And then I have a step in my shear force diagram. That corresponds to a point load. So by understanding the relationship between load and shear and bending, you can move from one to the other. And of course, they all have to agree with each other. So we got to the point, the shear force diagram. I also then briefly said, because we know V is equal to dm dx, when we draw our shear force diagram here for the case of a point load in the middle of the beam, how do we draw a shear force diagram? We start at the left side and we follow our loads. So we step up a value of our reaction P on 2, and as we move along the beam, we don't hit any load, so we just move horizontally across. And then this step down here will equal our point load P, and as we move across again, we hit no load. At the very end, we hit our reaction, we end up at 0, which is wonderful, because that means all the forces in the y direction equal 0. Now, to get from our shear force to our bending moment diagram, this positive value of shear here, P on 2, means our bending moment has a slope of P on 2. So when my shear is constant, see here, that means my bending moment will be linear. Because of this relationship, V is equal to dm dx, M is equal to the integral of V. When my shear is a constant, when you integrate a constant, you know you get Cx. So now you know there's a relationship. When your shear force is constant, your bending moment will be linear. And as I said, because we draw positive bending moment down, a positive shear force corresponds to a downward slope. So when I do these problems, I come along and I go downwards and upwards. Okay, I know where it slopes up and down. Then I look at my shear force and I say they're both constant, so I know my bending moment will be linear. Here is the case for the uniformly distributed load. If you look at the value of shear force here, it's changing. So that means my slope is constantly changing. It's changing from a big value to a smaller value, finally to 0. So if my slope is 0, what does that correspond? That corresponds, very messily written here, to a maximum value in your bending moment diagram. Okay? Because we're saying V is equal to 0, which is equal to dm dx. When is your slope 0? You know it's 0 at a maximum. So once again, you can move across here and say my slope is 0. That's when my moment is maximum. And have a look at the slope of this bending moment diagram. It's big, it's getting smaller and smaller, and then it's 0, and then it gets bigger and bigger and bigger. So that corresponds with the shear force diagram. If you understand these rules, you will work through them, and you'll be able to spot whenever you're wrong. Okay, so there is this wonderful table in the study guide, which is online. You don't get a hard copy anymore, but you can just print off this PowerPoint if you wish to. That basically tells you, here is the shear force diagram, here is the bending moment diagram. So when your shear force is horizontal, your bending moment is linear. When you get a step in your shear force, that means you get a kink in your bending moment diagram. Because these two values here that I've noted as C and D, the values of your shear, they represent the change in slope. Suddenly your beam is sloping, has a slope of C, and then it suddenly has a slope of D. So that corresponds to a kink. So whenever you have a kink in a bending moment, you know there's a point load there. When you have a UDL load, we know our shear force is linear, Cx, it has a function Cx, and thus, because of our relationship that M is equal to the integral of V, when you integrate a constant, you get some sort of parabola. So you know whenever you see a UDL load, you're going to have your bending moment will be some sort of parabolic, some sort of quadratic relationship. We don't cover that linear varying distributed load, but we do the applied moment. Anyway, we'll do a couple of examples, or what I'll do is I'll set them up, I'll give you a chance to attempt them, and then we'll work through this class, today's lesson this way. Okay, one final thing, or no, two more things to say. For a simply supported beam, and only for a simply supported beam, the bending moment diagram actually has the same shape as a hanging chain or a hanging piece of string. You get a piece of string, you put a point load on it, what's it do? Well, it follows the shape of all these red dashed lines. So all of a sudden now, any simply supported beam system, you straight away have your bending moment diagram. Okay, you know the shape of it. So this one here always bothers people. If these two loads are P, and you know you pull down with two even loads, your bending moment diagram through here will be horizontal. So can you imagine what happens if we have, I'll just put a value to this, a load of 10 and a load of 5. You have a piece of string, you pull harder with one side than the other. What's going to happen to your piece of string? It's going to come down, it's going to have kinks in it still, but it will look like that poorly drawn line. Can you see what I'm saying there? Okay, so easy peasy. Simply supported beam, easy bending moment diagrams. Just think of a piece of string. Okay, how do we draw a bending moment diagram? We always plot it on the tension or the stretching side of the beam. When I push down with my chin and look like an idiot, the bottom of this piece of moulding is stretching. The top is squashing. So that's telling me my bending moment diagram will be drawn on the bottom. When I have a cantilever and I push down with a point load, which side is in tension? The top, so I know my bending moment will be on top. If I have a simply supported beam here and I have a point load on the end, okay, can you see what side's in tension? The top, so we know our bending moment will be above the line. But when you come along and you apply a point load in the middle and a big point load, okay, you can see here I've got tension on the bottom here, oops, tension on the top there. So What's that telling you? That's telling you when your bending moment moves from one side to the other. So a point of inflection corresponds to where your moment is equal to 0. If I get some sort of shape like this, tension on the bottom, tension on the top, that means my bending moment goes from the bottom to the top. And that point it passes through 0 corresponds to the point of inflection in my bending moment. So here we have it here. We've got the case here where I just banged my chin or my nose or whatever it was, where we have 2-point loads on a beam with an overhang. So if you look at the red here, the deflected shape here, we know we have tension on the bottom and the tension on the top. Our bending moment, you wouldn't know yet, but looks as it's shown in blue, and thus where your point of inflection is, that corresponds exactly to where your moment is equal to 0. And that point here is our point of, at that point there, that's your POI. I write it as a POI. It's written out here in full down here. Your point of inflection. What is a point of inflection? Well, that's where you have no stresses, no bending moment. That's where you have tension on one side, changing to tension on the other side. So at that point there, you have no stresses at all. No stresses, no moment. Okay, let's draw some of these. So we always draw our bending moment on the tension side of the beam. Then we mark where the moments are known to be 0. At a pin or a roller end support, at a cantilever end, at a point of inflection. We know that now. Now I have just added this line in now, so if you've got these printed off, please add this line in. Or where you have a known value of a moment, and that would be at a fixed support. Okay, so where you know the moment, you put it in. Where you know the moment to be 0 or you know it has a particular value, mark them in. Then what do you do? Based on this wonderful relationship, V is equal to dm dx, we start plotting. So a positive shear force is a downward slope, a negative shear force means an upward slope. We said if our shear force is horizontal, our bending moment is linear. If our shear force is linear, our bending moment is a parabola. When shear is 0, our bending moment is a maximum. Now, if a very obedient student walked past this room and their maths was reasonable, without them even understanding what a bending moment diagram was, if they followed these rules, they could draw a bending moment diagram. So if they can do it without understanding, there is no reason why you can't do it with understanding. So please just follow the rules and you'll get it right every single time. Okay? And I say that because, you know, some of you always get them wrong, but there's no reason for you to get them wrong. Follow the rules. So the final point is, in order to calculate the value of the moments, we just integrate V. Do we have to have any mathematical equations and integrating? No, it's the area under the shear force diagram. So let's go back. We hit this problem last week where we had to draw the shear force diagram of it. So I'm now going to draw the shear force diagram for you again. And I'm going to let you, using the rules, work out the bending moment diagram. Now the next page is blank, so I keep these rules here. I'll just draw it up here. So our AY here value was 35 kilonewton, and our BY value here was 75 kilonewton. And our shear force diagram, we start at the left-hand end, we follow the loads. We step up a value of 35. As we move along this beam, we have no load change. Then we have a point load, so we drop down here a total of 30. So we're sitting at a value of 5. And now my load is reducing by 20 kilonewtons every metre I move along the beam. So therefore it must reduce by a total of 80. So therefore I have a linear drop down here, which would take me to the value of 75, and thank goodness my reaction is 75, so I move up. So there is my shear force diagram. Try drawing the bending moment diagram. So just to get you started on this, what shall I use? Purple, green, green. My bending moment at A, what's it equal to? What's the bending moment at a pin end support? 0. So my bending moment will be 0 here. What's my bending moment at my roller end support? 0. So my bending moment will be 0 here. I have a positive shear force. Which way will my bending moment slope? Downwards. So I'm going to break it up into 3 sections, okay? I have a positive value here. It's positive. Which way will my bending moment slope? Still downwards. Now my shear force becomes negative. Which way will it slope? Upwards. My shear force is passing through 0 here, so that's going to correspond to a maximum. Now, while you're thinking this through, I'm going to draw this up on the next overhead. I won't try freezing screens because it seems when I do it I freeze the wrong screen. And the people who choose not to come here miss out. And we can't disadvantage them, can we? Okay, so while you attempt to draw that, do you need the shear force diagram again? I'll transfer all that across here now. Okay, oops. No, which way am I going? Oh, I'm really making a dog's breakfast of this. Okay, so our shear force diagram looked like that. And the rule we're making use of is dm dx is equal to v. So as well as this being our shear force diagram v, now I want you to think of it as representing the slope, dm dx. So that was 35, that was 5, and that was 75. So we've set our bending moment diagram here. It will be 0 here and 0 here. Now, how is this thing deflecting? Just like that. I've got some sort of load on it. It's going down. Which side's in tension? The bottom. The bending moment is going to be on the bottom of the beam. So draw the shape. Draw it in your head if you don't want to draw it on paper. So imagine. And I don't want anyone playing 2048 or looking at a Facebook screen. Because my nephew, who is not in the class, attended last Wednesday's class and quite rudely left 10 minutes before the end. And he told me he can see all the screens. He said, everyone's playing 2048, Lizzie. So, I won't mention his name, that would embarrass him. So what did we say in our rules? Where is it 0? We know it's 0 here. We know it slopes down, it slopes down, it slopes up because my shear force is positive, positive and negative. And we know where v is equal to 0, that means dm dx is equal to 0, and that means there's a local, we usually refer to it as a local maximum or minimum bending moment. So, when my shear force is constant, what's my bending moment? Linear. When my shear force is linear, what's my bending moment? Parabola. So, that's telling me I come down like that. That's telling me I have a maximum here, and I've got a parabola in there, and it has to be a maximum here, and it has to continue to slope down. So the only shape it can be is that. Is that what you all got/imagined? Yeah, good. Okay, so in order to finish this, when you get asked to do these questions in the exam and the test, you get asked to define all values of local maximum or minimum values, which would be both these points. Because if you asked me to draw it, I'd say, well, how far do you want me to come down linear? And then what's the maximum as a parabola? So we need this value here. Now, if I need that value there, in actual fact, the easiest way to calculate that value there is to cut the beam there. So what's the value of the bending moment there? 35 times 4 metres. Is it not? Yep, which is equal to 140. But I also said if we want to use the full graphical approach, oops, I did that the wrong way around, I often do that, m is equal to the integral of v. It's the area under the shear force diagram. And what is this area here equal to? Lo and behold, it's equal to 35 times 4. It's amazing, isn't it? I know that's not what you intended, but I'm going to interpret that as pure amazement. 140 kilonewtons per metre, that's the easy point. How do you calculate this value here? You cut it, but where do you cut it? You don't know exactly where to cut it because you don't know that dimension or the other dimension, do you? But we do know that dimension, don't we? How do we know that dimension? Because we know W is equal to dv dx. So if I look at this triangle here, it has a height here of 75. This distance here I'll define as x. And this line here is sloping at 20 kilonewtons per metre. So can I now say rise on run is equal to hypotenuse? And do you know what I'm saying you understand what I'm saying when I'm saying that? So to find that value of x, I've got 75 kilonewtons over x metres is equal to 20 kilonewton per metre. So therefore that distance x, and I haven't got it written down. Have I got it written down somewhere? Well, x is equal to 75 on 20. What is it? 3.75 metres. Beautiful. Now, if I want to know the moment there, I could just cut it there at 3.75 metres and actually use equilibrium and calculate that moment. Perfectly valid way. But what did we say shear force is equal to? It's equal to the area under the shear force diagram. So what's the area of a triangle equal to? Half base times height. You can't see that colour. So it's equal to 75 times x on 2. And that will give you a value of... Oh, is that 140? The other one's 110. How come no one picked me up? Hang on. What have I got written here? At 4 metres. Oh, yeah, so I don't know what that value is, but you can work it out. Yeah? So is that easy? Good. Do the next one. This one. Same rules. So, hang on, can I put the rules on that page? Draw that, and then I'll put the rules up for you. Now for cantilevers, whether you need them or not, I would calculate the reactions. What's our reaction force equal to? Vertical force? 30? And what's our reaction moment equal to? Call that A. AM. This is now just to calculate reactions. Taking moments at A. I have AM minus 10 times 2, minus because it's going clockwise, minus 20 times 4 equals 0. So my moment, is equal to 200 kilonewton metres. Shear force diagram. What's it do? You start at the left-hand end and you follow the vertical loads. Yep, up, across, down, across, down. So what I don't understand is why in the lecture you all sit there going, yeah. And then I put it on the test or the exam and you can't do it. So, shear force diagram. We've agreed that's 300. Keep on drawing on your own pages. Shear force diagram. Oh, 30. Hang on, 30. Yes, I do. Sorry, I got carried away with the zeros in the moment. No, I was just checking to see whether you were awake. We start up 30. We come down to 20. We end up at 0. How does this thing deflect? Cantilever. Oh, people are doing that. Here. Fixed end. You be a point load, I be a point load. Point load, point load. Yeah? Which side's in tension? The top. So my bending moment will all be up here. So let's go back to these rules. I said I added in this. Mark where the moments are known to be 0. Where are the moments 0 here? At the end? Okay, so our moment is 0 here at the end. The question is, what is our moment equal to at A? Now, if I draw a tiny free body diagram here, and this is A, and this moment is 200, and I've exaggerated this, but this length in here is 0.0001 millimetres. What is my internal moment equal to? Well, it'll be going equal and opposite, won't it, for equilibrium? So it'll be 200. So, at a fixed support, the internal moment is always equal and opposite to the reaction moment. The moment at a fixed support isn't 0. Can you see it's curving here? You can see physically the circle, it's curving. So at a fixed support, the moment isn't 0. Now I say equal and opposite to the reaction moment. You don't say that moment is positive, so my moment in my beam is positive. The way I've drawn those 200s now, here's my reaction moment, here's the moment in my beam. Is my beam happy or sad? Sad. So my moment is negative. So therefore, the moment here, have I got red? Yeah, I am on red, aren't I? The moment here is, whether you put plus or minus in, I don't mind, because we know we draw positive down. So this moment's actually a negative moment. Why is it negative? Because our beam is sad. So very important, even though I wrote it out really messily, at a fixed support, the internal moment is always equal and opposite to the reaction moment. Okay, I've got a 200, I've got a 0. My slope is positive, so it's sloping down. My slope is positive, it's sloping down. This, as well as being the shear force, is dmdx. So this is telling my slope through, let's call it ABC. Through AB, the slope is 30. Through BC, it's 20. So, are you all drawing something that's slopier here than it is there? Did you all draw that? Yes. Yes. Good. So I can easily put something like this but different on the test and the exam and you'll all get it right. Okay, so one thing we're missing, we still need the value of the moment here. Now, if we could use the area method, what's the easiest way? What's the moment there equal to? Yeah, but why don't I just say I'm going to cut the beam here, it's 20 there, I want to know what that moment is equal to. What's the moment equal to? 80, 20 times 4. Now the reason I point that method out is the area under the graph. If you start at this side, we're going to get an area of 30 times 40. We're going to get an area here of 120. If we work on this side, we're going to get an area 2 here of 80. Those two areas unequal. What's going on? Whenever you have an internal moment equal, the moment here is going to equal your minus 200 plus area 1. So you have to take the area away from any moment acting. When you come from the right side, because there's no moment acting in there, when you come from the right, it's always the negative of the area, by the way, area 2. So please don't think what people do here. Have I got a blank page? I'll come back to this in a minute. What people do here is they draw the shear force diagram like that, and then they say that area, oh, my bending moment is 0 here, and the area, so they draw me a bending moment diagram. Oh no, it's a positive area that does that. Now, can you see how much that would, I can't swear, annoy me? Okay? Because when people draw a bending moment like that, they say, what's wrong with that, Lizzie? And then I have to go through, what is wrong with that bending moment diagram? Is it 0 at the tip? No. Does it have a value at the fixed support? No. Am I drawing it above the line where I expect it to be because of the deflected shape? No. So if you're not sure about something, go back and answer all your questions. And so that is wrong. So when we come back to the value we've got, you can also draw your deflected shape in here. Oh, I've got tension on the top of the beam. My bending moment is above the line. My bending moment is 0 at the tip. It has a value at the fixed support, equal and opposite to my reaction moment. It's a positive value, it's sloping down. It's a positive value, it's sloping down. It is all in agreement. So, shall we try a harder one? So we've done simple supports, fixed supports. Now let's do a applied moment. Now, I will admit, I am aware that some of you probably won't even, at this point, and that's okay, be able to calculate the reactions here. Oh no, we will. Let's calculate the reactions. AB. Before we start this problem, before you start any, you need the reactions. Okay, let's take moments at A. And when we calculate moments at A, we're going to solve for B1. So taking moments at A, it's my 200 newtons times 16 metres. That's going clockwise. So it's minus. Then I have my BY times 8 metres. That's going anti-clockwise, about A, so it's plus. Then I have my moment. My moment's already a moment. So am I going to go plus or minus 800? Plus, because it's going anti-clockwise. So from that, why did I write 16? What did I write? That's metres. Okay. So I've got BY. When I solve for BY, I get a value of 300. So that value there is 300. So that means my AY is pointing down and has a value of 300. So when you look at all your forces, can you see you've got the reaction down? So why is that reaction down? Just if we look at the point load, can you put a point load on the end again? If you put a point load on the end and I let go here, what happens? It flips up. You're not applying a very big point load. It flips up. So what this reaction is doing, it's pulling back down to balance that. Okay, draw that shear force bending moment diagram. Is an applied moment a vertical force? So does it affect the shear force diagram? No. So no matter what combination of loads or forces or anything, it follows the same rules. You want to get full marks, make sure you put your units. Usually the easiest place, thank you. And make sure you put the correct units. Because if you look at this system here, the forces are all in newtons. Oh, here. Oh, and here. Yeah, good. You're all on the ball. I'm not. So it's important to put units on. It's important to put correct units on. As I said, you can't stand up in court and say, I got all the numbers right. Fortunately, I got them wrong the wrong way. I was being more conservative, so the building wouldn't fall down. I would just never work again because it would be so over-designed. It wouldn't be funny. Shear force diagram. Which way do I go? Down. Across, up, 300, that takes me up to 200, across, down, I end up at 0, I'm happy. I don't end up at 0, I've made a mistake. Now I do have an applied moment here, so it's a little bit trickier than you would expect. But where is our bending moment 0? Is it 0 at A? It's a pin end support. Yeah, it's got to be 0 here. Is it 0 at B? No, I said a pin end or a roller end support. If the beam, can you imagine the beam is curving? If it's curving, there's a moment in there. Is it 0 at C? Yes, that's a cantilever end. No, you're just... Maybe you're not playing with me. No, it's 0 at a cantilever end, unless there's an applied moment there. So I've got 0, 0. I have a negative shear force, it's sloping up. I have a positive shear force, it's sloping down. But I have a moment acting in there. So see how far you can get. To pace myself, I'll wait till it's on the 447. Try it. So you can do it like a join the dots. Start where it's easy and then stop at the hard bit. So I would start at NC. There's no moment there yet. I'd start at NC, it's 0 here, and it's constant, so this is linear, and it has to slope up. So that all agrees. So what's the value of my moment? That area in there. 8 times 200. Or I can just imagine I've cut the beam at 8 metres. It's almost easier to imagine you've cut the beam at 8 metres. So that means this value here is 1600. Did you get that right? It's constant. So the slope of this line here is equal to 200. Now, I go to the other end. Looks a bit tricky now. I know it's 0 here and it has to slope up. What slope do I put on it? Well, I know the slope's 100. Over here it was 200, it's 100. So I'm just going to take it up to the moment because I'm not sure what happens at the moment. So up until that 4 metres, what's the value of my moment here? Just 400. Well, it's that area in there. Or you just cut the beam at 4 metres, 400. Now, a bending moment, and you know what I'm going to do, it is 400. I just have to draw this more to scale because it won't fit in there. So 400 will bring it about there. When you have a point load, that causes a step in your shear force diagram. When you have an applied moment, that causes a step in your bending moment diagram. So my bending moment here, it's 800. It's up to you. How do you remember that an anti-clockwise moment is a step up? But an anti-clockwise moment is a step up. So that steps up to 1200. And that fits in because I'm still sitting below my 1600 because my slope still needs to slope upwards. And when I do slope upwards, I match up with that 1600. People come close? Pardon? You got it exactly. For all those people that got it, pat yourself on the back. Well done. Okay, the next problem is similar but different. It looks the same, but I just want to show you how it can be different. So the next problem has, instead of a 200 at the end, an 80. So I'm quite happy to tell you that the reactions here would be 60 this time, and this time at this end the reaction is 20. Oops, and I'm doing kilonewtons again. So same dimensions as before, same applied moment of 800. Oh, actually before we pause, can you imagine what that deflected shape looks like? If you can't, go to your bending moment diagram and say my bending moment is all above the line. So I know I'm going to have tension on the top of the beam throughout. So even though you might be tempted, so do you understand what that 800 is doing? Can you be a pin support? What that 800 moment is doing is that. Okay? It's actually rotating the whole beam 800. So what's this deflected shape look like? It's very tempting to draw that. Oops, it's got to be 0 here because it's a support. Why do I know that's wrong? Because I've got tension here and I've got a point of inflection here. And my bending moment diagram is saying, no, I've got the tension on the top throughout. So that is wrong. My bending moment diagram, I have to listen to my bending moment diagram because my bending moment and my deflected shape agree. So basically, and I haven't drawn this very well because the deflection has to be 0 here and here, it must be deflecting down. So that point load on the end, so basically we've got, can you be a support? You be a support here. So he's pushing down here, and I'm applying a moment, but it's not enough of a moment to cause that inversion, that point of inflection in there. I'm applying a moment, but it's not enough, that point load on the end. Okay, so draw the shear force and the bending moment diagram. Shear force is easy enough. Rather than rush this one through, I do want you to all think about it. So bring it back on Wednesday with values. Okay? So draw the bending moment diagram. Remember the rules we're going to make use of is V is equal to dm dx. Oops, sorry. And I'll see you all on Wednesday.